Hello, everybody. Today we're going to be presenting the FortisAVQA and MAVEN paper, which is a benchmark dataset and debiasing framework for robust multimodal learning. I'm Salma Taslim, and I'm going to be presenting this paper with my co-presenter, Lu'ay Wali. So first, before we get into it, we should understand why audio-visual question answering is even important. So as the name suggests, it's basically answering questions based on both audio and video data. In terms of real-world relevance, this is relevant to a lot of applications, for example, smart assistants, robotics, and accessibility. So imagine, for example, a visual impaired person using a smart assistant. They would need this assistant to be able to capture both the visual data and the audio data and be able to make decisions based on both of them. The challenges with this is that it requires understanding and reasoning across modalities, which is often difficult than just using one specific type of modality like images or audio or even just text. So the current problem with AVQA data is they often have biases and they learn shortcuts. Example, providing answers based on just the text questions. So models would often learn answers like yes to questions that start with is. So is there a violin? They would just say yes, even if there isn't a violin, because they're not actually using the audio and the visual data and they're just learning that statistical shortcuts. They often struggle with rare or tail distributed questions or rephrased questions that differ linguistically, but they have the same meaning. So is there a violin or is there a violin in the video, as well as out of distribution data that differs from the training distribution and the questions that the model is used to. Another problem with AVQA dataset is they lack benchmarks that test these robustness aspects. They often just get tested on the specific same type of questions that they were trained on, and so we're not able to check for this robustness. And before we dig deeper into the construct or contribution that this paper proposes, let's try to answer the following questions. That have the existing AVQA datasets comprehensively measured model robustness, and have the existing methods like overcome this data bias? So for the first question, it's important to look at three types of issues. First is template limitation. So a lot of AVQA datasets like the MUSIC-AVQA, they use a small set of predefined templates. So they have templates for the questions, and the MUSIC-AVQA specifically, it uses around 33 templates, which results in a very limited linguistic diversity. So they'd have a template that would only make the question, what is, insert there. Additionally, this also causes the dataset itself to have small vocabulary. So the templates, they lead to a very narrow vocabulary. In MUSIC-AVQA, for example, this is only around 93 words. And this doesn't represent real world data where there are a lot more words and a lot more things that can be there in video and audio data. And lastly, there's a lack of rare cases. So the current datasets, they're lacking the rare and less common samples. And this means that we're not evaluating our models on uncommon scenarios, which are pretty common when it comes to video and audio data. And for the second question of how the existing methods overcome the data bias, a lot of models struggle with model brittleness. So existing models and methods like the SDG, for example, which is spatiotemporal graphing, they struggle to answer questions that have rare answers. And they also tend to memorize answers. So they tend to memorize statistical patterns between questions and answers instead of relying on the actual multimodal inputs that they're receiving. And this leads to unimodal accuracy. So experimental results, for example, they show that models like SDG, it yielded accuracy of about 54% without any multimodal input. So this means that it was just memorizing a pattern between the question and the answer, rather than actually taking into account what video or audio it was receiving. And so the first proposal that this paper proposes is the FortisAVQA dataset, and we'll be describing what this is. So an overview of this dataset, it's a novel dataset that has with it a comprehensive set of evaluation metrics. And it's built by rephrasing the questions that are there in the MUSIC-AVQA dataset, which we mentioned relies on a template, in order to increase linguistic diversity. So what it contains both in distribution, which means data's like questions that MUSIC-AVQA already has, and out of distribution test questions. And it contains rephrased test questions that are evaluating linguistic robustness. And it's designed to expose like overfitting and test the true multimodal reasoning of any AVQA model. In order to construct this dataset, it went through two main stages. First of all the questions in the MUSIC-AVQA were rephrased. And this was done by taking one question in MUSIC-AVQA and using LLM in order to generate like 25 types of that same question. And then those generated questions were passed on human annotators, which checked for its accuracy. The second stage was introducing distribution shifts, and this was done by splitting the questions. So taking any question and seeing whether it was frequent, so a question that the model would usually get, or rare, and this was called a tail question, and based on the answer frequency and constants. So in order to be able to visualize how this test set or how this data set was constructed, here we have a visualization that's visualizing the rephrasing state. So on the right, you see a template. On the left, you see what is the instrument of the left or right of object. And this is how a template would look on the MUSIC-AVQA. So an example question in MUSIC-AVQA would be, what is the instrument on the right of piano? The rephrase questions could be anything like, which instrument can you make out to be on the right of the piano? The MUSIC-AVQA dataset didn't have this type of question. And so if you look at these circles, they're basically telling us the frequency of words that could come after a specific word. So for the FortisAVQA, you can see that there are many different types of words. And this kind of like depicts that there's many types of words that could exist after it. However, when you look at the MUSIC-AVQA, there's only a set specific type of words that whatever model that you have for audiovisual question answering can be trained on. And this creates the biases that we talked about earlier. And so the goal behind FortisAVQA is to inspire the community to enhance model robustness and to focus on that through the implementation of debiasing strategies rather than striving for a balanced training data. And so a second question that arises is, how exactly do we debias?
And this is where the paper's second proposal come in. Basically, they have proposed an MAVEN model, which is a multimodal transformer-based encoder-decoder network. It is, as they have mentioned, the first bias mitigating generative AVQA architecture, and it utilizes something called the MCCD debiasing strategy. So what is the MCCD debiasing strategy? Basically, it is a novel optimization objective that aims to increase the distribution gap between the unimodal and the multimodal logits. By this way, we are going to be encouraging our model and enforcing it to rely on multiple modalities instead of just relying on one modality. And they have also proposed a way to improve the distribution gap enlargement way. Instead of relying on normal metrics like the L2 norm and the Euclidean distance, they have evaluated and enlarged the distribution gap using the KL divergence, which makes more sense and more accuracy when you are talking about comparing two probability distribution together.
So now we're going to talk about how they evaluated this model through the evaluation and ablation studies. So an overview of the evaluation that they performed, they used two main datasets mainly, the MUSIC-AVQA and the FortisAVQA. The MUSIC-AVQA, it's the original template-based dataset with the known biases that they're trying to tackle. The FortisAVQA is the new dataset that they propose with the rephrase questions as well as the distribution sets, and it's designed to rigorously test model robustness specifically. In terms of evaluation metrics, two main metrics were focused on. First of all is generalization. So how well do the models perform on both in distribution, so head and more frequent questions, as well as out of distribution, which are tail or rare questions. In terms of robustness, they were looking at, can the models handle these rephrase questions in rare answer types, or are they just memorizing some patterns from the training data? So in metrics in general, they relied on task-specific accuracy, and task-specific accuracy was as follows. There was audio QA accuracy. So these are questions that can be answered from the audio alone. So is there a violin sound playing as an example of this? Visual QA, questions answerable from the video alone. So is there a violin in this video? And AVQA, questions requiring both. So what time did the violin start playing, or was there a violin that was playing, which requires both there to be a violin as well as the audio to be measured. And robustness metrics, and these looked at head accuracy, so their performance or accuracy in general on frequent or in distribution questions, as well as tail accuracy, which is the performance on rare or out of distribution questions. And they also measured overall accuracy, so that's the combined performance across all the test questions. So they compared these with baseline models. They compared the MAVEN model with baseline models. So they evaluated 12 recent multimodal question answer models, including both small and large models to make a comparison. Some of these models are the LAVIT model, which is a relatively smaller model, the Video Llama 2, which is a relatively larger model, and the MAVEN, which is the model that they're proposing. So the key findings is that they found that MAVEN and Video Llama 2, which is the larger model, they showed the smallest performance drops from head to tail. So when they used head and tail questions, it was only around 1.68% and 5.71% drop respectively. And then baselines like LAVIT, which are generally considered to be good AVQA models, they drop sharply on tail questions. Example, 22.2% on the exist question. So is there a violin, for example? Questions like that. And for MCCD debiasing, they've shown that it actually improves robustness for 7 out of the 9 models when tested on the FortisAVQA dataset. So the conclusion that they made was that high MUSIC-AVQA scores, accuracy scores for different types of tasks, they don't guarantee robustness. So even if a model performs really well in terms of the multimodal task, it doesn't mean that the model is actually robust. And using the FortisAVQA dataset as the testing dataset and the training dataset exposes this overfitting to specific biases. Another study that they considered that is important to consider is ablation studies, and to be able to see whether removing different parts of the MAVEN model, does that contribute to the general performance. So what they found that removing audio regularization, it causes the largest performance drop, especially on tail-rear questions, which shows us the importance of audio in actually answering audio-visual questions, and that's usually what the model might compromise on. Secondly, that each debiasing component, so audio, video, cycle guidance, or using them both, is important for robustness. And lastly, that removing any component leads to significant accuracy loss on the out of distribution. So in order to actually answer questions that are less frequent, the model needs to be able to take advantage of both the audio and the visual data. And lastly, it's important to talk about hyperparameter sensitivity. And so the main 2 hyperparameters that they talk about in this paper is alpha and beta. So alpha is diversion strength, and it controls how much the model avoids relying on statistical shortcuts. So memorizing the is music playing and usually means yes. And here it relies on KL divergence. Well, they found that the best accuracy happens at alpha around 0.001. And if you have a value of alpha that's too high, the model will aggressively reject answers based on single modalities, even though they might be right in that specific use case. So is there a violin? You might just need the video data, but the model would reject the answer being yes in that position. As for the second parameter that we have, it's cycle constraint, and this ensures the alignment between audio, video, and text. So for example, linking like violin sounds to violin visuals. And so if this is this being too low, it means that the modality is misaligned. So for example, like mismatched audio visual pairs. So is there a violin? It won't look for a violin visual. It will just look for an audio, for example. And if it's too high, it'll force like unnatural alignment. So it will break like real world reasoning. And so it's important that these parameters are carefully tuned in order to have maximized robustness as well as like accurate performance.
So, and then we are going to be talking about the methodology. What is actually the MAVEN architecture that we are have been talking about for some time, and how does the debiasing actually happens? Here is the MAVEN architecture. It might seem a little bit complex, but we are going to be breaking down the generation step by step and the architecture block by block. First, the MAVEN architecture extracts a unimodal embeddings using modality-specific encoders that we are going to be talking about in the next slides. After extracting the unimodal embeddings, we are going to be fine-tuning a parameter shared generative model that's going to be learning the multimodal fusion between the unimodal logits, and then it will be like generating the answer based on this fusion. And after that, our debiasing comes in, which is only like happens during training. The debiasing strategy is applied like with like 2 different things that are being done simultaneously. First, we are amplifying the disparity between the fusion logit and the bias logit. In other words, the difference between the multimodal logits and the unimodal logits. And at the same time, we are applying a cycle guidance mechanism to ensure the consistency among the bias logits. In other words, to ensure the consistency among the unimodal representation, the unimodal distributions. For the unimodal representations, how are we going to encode videos? Basically, we use a fixed or pre-trained internal VIT with a 300 million parameters. It takes the video and generates a 256 token embeddings. And for the audio, it might be a little bit tricky, but let's break it down step by step. First, they employ a mel filter bank block, which decompresses the audio segment into individual frequency bands. And then the extracted audio features are passed through a downsampling convolution neural network, which is like consists of 4 layers. And by this, we are going to be reducing the input dimensionality, but while preserving some crucial temporal and spectral information. And after that, the output audio features from the convolution network are going to be passed through a stack of 24 pre-trained transformer layers with fixed parameters. The transformer layers are going to be pre-trained on a large scale speech recognition and audio captioning datasets. And this gives the capability of the transformer layers to capture long-range dependencies in the audio sequence and also model complex temporal relationships. And after we get like our embeddings for the videos and for the audio, we are going to be doing some sort of modality adapting by like adding a trainable MLBs after our encoders. Then it comes to the answer generation part, which is the most important part in our network. We are going to be treating the video and audio and text as token embeddings as we have like extracted them earlier. And we are going to be adding a special token for each modality, like for the videos, there is a special token, and the audio it has a special token and so on. And then we are going to be fine-tuning a VITA model to integrate all of these modalities because the VITA models do not like utilize the three modalities at the same time. They usually rely on like two modalities together. And then we have like generated our answer and so on, but still we did not do anything regarding the debiasing part. Basically, we are doing a unimodal bias learning because biasing some design, I mean, like individual modalities have biasing in them. So we are going to be learning the biasing in the video and in the audio and in the text, and we are going to be using them in the debiasing next. For the debiasing, we are having our divergence loss and cycle guidance loss. And for the answer correctness, we are going to have the answer loss. By this, we are going to be ensuring that the model predicts the correct answers. And at the same time, we are going to be ensuring that the unimodal and the multimodal outputs are different. And at the same time, we are going to be ensuring that our unimodal distributions are consistent with each other. So how are we going to be training our model with all of this, like the big architecture and the multiple loss and so on? First, we are going to be extracting our unimodal representation, and then we are going to be fusing them together and generate an answer. And this is the first part of our network. The second part, which is learning and capturing biasing in the unimodal logits. And then we are going to be calculating our loss, which is answer correctness loss, and the debiasing loss, which is the KL divergence one and the cycle guidance one. And then we are going to be adding these three terms together and performing a gradient descent to update the parameters of our network. So our conclusion, what does this paper propose and so on? First, they propose the FortisAVQA dataset, which basically is used to measure the preciseness and the robustness of the models across like an unseen data, like the head and tail, common and common questions. And also they have proposed the debiased network, like the generative MAVEN architecture with the MCCD debiasing technique. And they have also like compared it with the previous question answering models, and they have proved that actually the debiasing with the network have actually made the accuracy very higher. So to summarize the contribution of this paper, first for the dataset, they have taken the MUSIC-AVQA dataset and they have rephrased the questions and then applied some sort of distribution shapes to ensure that we have like two separate types of questions, which are the head and tail questions, common and uncommon ones. And then this is what they have called the FortisAVQA dataset. And next is the MAVEN architecture with the debiasing framework. They have trained it on the biased training dataset, which is the MUSIC-AVQA dataset. And then they have tested it on the new unbiased test set of the FortisAVQA and like started observing the accuracy and so on. So this was the paper. Thank you all for listening. Luay and Salma was with you.